So we're talking about this important problem in calculus. You know how fast a quantity is changing at every moment. You want to know how much of it you have at every moment. And so we've been really looking at this flag, the height of the flag as the quantity, right? You know how fast a quantity is changing every moment. We're looking at this example of height of the flag. But it could be lots of things, right? It could be the volume of something that's changing. It could be temperature that's changing, distance traveled. Any quantity that we measure, scientists, mathematicians measurement, fall under this category of you know how fast a quantity is changing, and so based on how fast it's changing, we want to be able to kind of create or develop a profile of how much we have at every moment, right? So you know how fast a quantity is changing every moment. You want to know how much of it you have at every moment. So what is this graph I'm showing you in relation to that? What is this graph that I'm showing you over here on the left? What is that? The rate of change of height. You know how fast the quantity is changing every moment. We know how fast the height of the flag is changing at every moment. Here it is. And what is our goal? How much we have at every moment. And the first thing we did was just we kind of did a rough sketch of this. We said based on that rate function, what would that like in this case the net accumulation function look like, right? It's tracking what? How much change in height since 0.6 seconds. And we made a rough sketch of that. So this whole endeavor, this whole first week is about, you have this function on the left, and you want to kind of construct or develop or create this function on the right. Okay? Not just as a rough sketch, but now like as an exact function, as a formula. Okay? So how do we do that? So this is what we've been working on. So what did we do first? So we started with what? Exact rate of change. What came first? Exact rate of change function. Okay, and that exact rate of change function, we called that little r for rate, and then exact, so of what? Exact of the height. So this is the RH function. And so function notation might look something like this. So for example, r sub h of 1.3. And what would that mean? What would all that notation, all that symbolism mean? R sub h of 1.3. The rate of change of height at 1.3 seconds, right? So this whole notation, so we've been working hard on it. We'll continue to work hard on function notation. That whole thing, that whole expression means the rate of change of the height of the flag at 1.3 seconds. And it's perfectly good on its own, but if you had the function, so this is actually this function right here, if you had it, you could actually find a value, right? You could find a value by using the formula. But you could just write r sub h of 1.3, and you don't have to find the value. It still stands for that value, okay? All right, so that's our exact rate of change function, r sub h. And what do we do next in our journey towards creating the net accumulation function? Where do we go from there? What was next? Do you remember? How do we make progress towards this? Yes, please. Right. So we said, what's difficult about this? The rate is always changing. But we know the math for what? A constant rate of change, right? We can get little changes in height if the height was changing at a constant rate. So we create a pretend rate function. We use interval sizes of 0.35 seconds. We did a pretend rate function, putting a constant rate in every interval. Remember doing that? So that we could have something to calculate changes in height, right? Because if the rate is constantly changing, we have no way of calculating a change in height. But if we have constant rates, we can get a change in height, or changes in height. And so we created this pretend function based on constant rates. Okay, so this was called the pretend rate function. And that we use the just little r. So little r then means the pretend rate function based on the exact rate of change function. Okay, and so we did two different ways of doing this pretend rate function. The first time we did it, we looked at each interval and we tried to eyeball kind of like the best average, right? And made that the constant rate for the whole interval. And then we said, well, maybe a more systematic way would be pick off the actual rate at the left side of every interval and let that be the constant rate throughout the whole interval, right? So this is showing the left method, right? This is showing the left method. In your homework, it says you have to do this, and it says something like, create a pretend function based on your best guess at, what would be the best estimates. So would that be like the eyeball average method, or would that be the left method in your homework? Would you be using the eyeball or the left? So just read the instructions carefully. You got two choices, okay? Based on reading the instructions carefully in that homework, does it imply that you're supposed to be like kind of looking at all the rates and kind of trying to pick the best one, like an average? Or does it tell you that you should use the left method? Okay, read the instructions carefully. Okay, so we got the pretend rate function. And based on the pretend rate function, last time in class, we were able to come up with a net accumulation function by creating a linear function for each interval that keeps track of a running total of change, right? Running total of variation. And at any given point, what that value of net accumulation is what the sum of all the changes from the completed intervals, remember this? The sum of all the changes from the completed intervals, mdx for the first interval, mdx for the second interval, mdx for the third, plus a little bit more for the current interval, m delta x. These would be all m delta x's for completed intervals. And then m dx for the current interval, right? dx is that changing variation in the current interval. And so based on the fact that, so for any given time, so here's x, right? So for any given time since we started lowering the flag, we add up all the change from the completed intervals plus a little more change from the current interval, and it gives us, should have done it the other way. Do it again. So that right there, what is the net change in height, or r sub h, or sorry, r, just r of x. And that y value of that function right there, again, the sum of all the change from the complete intervals plus a little bit more change from the current interval. And so then we get this point here, x, r of x. Okay, so after the pretend rate function, we put together what? A approximate accumulation function. And we call that capital A. So this is not r of x. R is the blue one over here. That's not r. If you were thinking that shouldn't be r, that was good. This is a. This is the a function. So this is x a of x. X r of x is over here. X r of x is this point here. And so what do we say? We said that a of x function was what? The sum of all the change from the completed intervals, right? So we get the change in height from the first interval, the change in height from second, change in height from third, fourth, etc. And we add all those up. That's what the Greek sigma means, plus a little more change from the current interval. And if you were in Dirac Calculus 1, if you had Bonney or Mahosky in Calc 1, you spent a week or two developing all the details of that. This is kind of a skeleton, just a skeleton. But in Calc 1, if you had this version of Calc, you really dug in and you got this down to the letter. So this is just a skeleton of this approximate accumulation function. Okay, questions so far? Questions so far? So this is review. So then we said, okay, that's all well and good, but what do I want? I want we're trying to get whatever this mysterious exact accumulation function is. So we don't know what it is. We have an idea. We made a sketch of it, but that's what we're going for. So where do we go from here, from this approximate accumulation function, to move closer towards exact accumulation? What do we do? Yes, sir. Yeah, so with a smaller time interval, our rate function will do a better job pretending to be the actual rate, and then therefore the accumulation function will do a better job, or be closer to whatever this final exact accumulation function is. All right, so let's do that. So this was our, so I'm going to hold on to, that's the accumulation function for 0.35. And so we'll do a better, here is 0.1775 for the time interval, for the new delta x, 0.1775. And so watch what happens. So these are shorter time intervals for our delta x's. And so the approximate rate of change is better than it was before with smaller intervals. And so then this thicker is this is the new approximate accumulation function. And because the pretend rate is better, that's better, right? That's going to be better. But how does it compare to the last one? Is it the same as the last one? There's still a big difference, right? Because we have because the two approximate accumulation functions are significantly different, that means we're not close to exact yet. So how do we do better? So what was this? 0.1775. I'll come here and hold on to our best version so far with intervals of 0.1775. And I want to do better. What does that say? 0.0395. Okay, 0.0395. Let's take a look at that. So here's intervals of 0.0395. How's the pretend rate function look? It's getting good now, right? So this is like it's reproducing that exact rate really well. Okay? Is there a distinction between the last approximate accumulation function and now the current one based on intervals of 0.0395? Still a little bit different, right? Still a little bit different. What does that tell us? We're not close enough to call it a day and say it's exact. So what do we do? So that was what? 0.0395. We'll hold on to that one. And we'll be even closer. So now let's get super close, right? So super small. So like 0.005, okay? So our last interval width was 0.0395. Now we're at 0.005. Here we go. Watch it. All right, how about the new step function? How about the new approximate rate function? Let me turn on, let's see. How do I turn that off? All right, I just turned off the exact rate, and I just have the new approximate rate. How's it look? Those are actually little constant rates. Those are actually little steps, right? If you squint your eyes, you can't tell the difference. So with an interval width of 0.005, it's so close to the exact rate that we might say that this is good enough, right? These intervals are so small, and it's reproducing the rate function so well that we might quit at that. All right, what about our comparing the last two approximate accumulation functions? You see there's really almost no difference now. Okay? These are almost the same. So when your intervals get small enough that if you make it any smaller, you don't see any difference anymore, then it's kind of like we're kind of have arrived at what's essentially the exact accumulation. So how small is small enough? It's small enough as if you make the interval smaller, it doesn't help. It's basically kind of arrived at this convergence point, right? You've converged on something. Then we call it a day. We say we're close enough. With really small intervals, we've got the exact accumulation function, okay? And so we call that. That's number 4, the exact accumulation function. And so we'll go back to putting a subscript. When you have a subscript, it's exact. When you don't have the subscript, it's non-exact. So this is A sub h. Okay, and so let's see. So what happens? When delta x is so small, there's really no distinction anymore between dx and delta x. And so this becomes, so for when the delta x's are really small, then what we used to have as the partial interval, it's kind of really just like the last completed interval, right? Because the delta x is so small. This kind of gets absorbed into this as the very last one of the completed intervals. It's like everything's a completed interval when that width is so small. So A sub h of x is just like this. It's the sum of those with delta x really small. Okay, but we have another notation for that. We have a shorthand notation for that. And what is that? So when the intervals get really, really small, how do we represent accumulating and keeping a running total of all the little changes in height? Remember what that is? From Calc 1? Instead of sigma, we use integral, right? This is what an integral is. This Greek sigma means sum, and so does the integral sign. It's German S for sum. Okay? What are we summing up? We're summing up changes in height, but it's kind of like for every value of rate, right? Because those intervals so small, we want every value of rate. So now we're back to R sub h. And then dx. Okay? In our particular example, where did we start accumulating? 0.6. And we're going to accumulate until x, whatever the x in question is. All right, but in order to do that, for any given x, we need to let time vary from 0.6 up to x to accumulate all those changes. So we need a different symbol here. Rather than x is inside, because this x stands for where we're accumulating to. But to do that, we start at 0.6. We got to accumulate all the little changes from 0.6 to x. And so we don't want to use x here to mean the right right end of it, we need a different symbol, so we'll just use, say, t. So t is all the x values from 0.6 to x. So we actually accumulate at all those different rates between 0.6 and x. So this is our exact net accumulation function. The integral from 0.6 to x of what r sub h of t dt, that right there is a little change in height, and we're accumulating all those changes starting from 0.6 to x. That's what integral means. Okay, so then the next step here is the goal. The goal was how much we have. So net accumulation in height is really close to what we want, which is actually the height of the flag. So how would I, if I have all the changes in height since 0.6 seconds, how would I then write the height of the flag, which is just an h of x? So h of x is the height of the flag at any moment. The height of the flag at any moment. How am I going to get that? I'm just one simple step away. If I have all the changes or variation in height since 0.6 seconds, how would I write the height at any time x? One step away. Anybody? How would I get the height? Yeah. And why would you do that? What is h of 0.6? Yeah, so h of 0.6 would be the height at 0.6, right? And so from there, if I started adding how much the height of the flag varied, then I'd always have the height of the flag, right? This is telling me, this function tells me how much the flag went down at any time x. So if I include the starting height at 0.6, and then add on how much the height has gone down at x seconds, then that would give me the new height. Should make sense. Good job. Was anybody else thinking that? Not saying it. Okay, so, and then maybe a more convenient or more natural thing to do would be instead of starting at 0.6 to start at where? 0, right? So start with the initial height at 0, but then we'd have what net accumulation function? Changes what? Starting from 0. So we're going to instead start accumulating at 0. But either one of these is valid. It's just maybe a little more natural to, let's start with the actual height when time starts, and then we're going to track the changes in height, or the amount of decrease in height, and that will give us the height of the flag at any moment, right? At any moment x. So I didn't write what 5 was. What is 5? 5 is exact. So this should have been exact what? Net accumulation. That's our a sub h function, meaning amount of change since a certain point. And then 5 is exact total accumulation. So you know how fast a quantity is changing at every moment. Which function? 1, 2, 3, 4, or 5? You know how fast the quantity is changing at every moment. Which function is that? 1. You want to know how much of it you have at every moment. Which function is that? You want to know exactly how much height you have at every moment. 5, right? So you know how fast it's changing at every moment. 1. You want to know how much you have at every moment. 5. So this is this journey through these different functions to get from your exact rate to your exact total accumulation. You know how fast it's changing? You want to know how much you have. You know how fast the height is changing? You want to know what the height is at every moment. Okay, any questions? Any questions on that? So let's summarize let's just kind of summarize this all again in some nice slides. here we go. Before I move on, any questions? I did a lot of talking there. Did you keep your brain on? Were you following? So you got the video. Go back, pause it, take good notes, listen to my explanations again. So this is super important. This is the kind of the basis of half of calculus, right? This is like the basis of half of calculus right here. Okay, quick. Here we go. Principle 1 was constant rate of change. 60 miles per hour means not just how far you go in 1 hour, but in any amount of time, right? You know how far you go in any amount of time. For any variation in time, the variation in distance would be 60 times that change in time. And that's important because we kept changing the interval size, right? We started at 0.35 seconds, and we made it smaller and smaller and smaller. So we need to know how much change in height for any amount of time. 0.35, what did I do? 0.1775, 0.0395, 0.005, right? I kept making those intervals smaller. And so it doesn't matter. I can still know how much change in height I had if I know the rate, right? Net accumulation function. It gives how much change in a quantity at any value x when the rate of change is known. That was principle 2. And then we said realistic rates are changing rates. We started with a constant rate for the flag coming down, but we said it's more realistic oftentimes in life that the rate changes. Okay, so we built a pretend rate function. We're going to mimic the rate function with constant rates so that we can use dy equals mdx, right? That's based on constant rate. So we're going to make this pretend rate function out of steps so that we can use dy equals mdx to calculate little changes and put together the accumulation function. And that was the skeleton of it, right? What? The sum of all the change from completed intervals plus a little bit more change from the current interval. All right, so what did we say? Next interval principle was to make more smaller intervals to make our approximations better. Better pretend rate function, better net accumulation function. Better ingredients, better pizza. All right, so that was that, right? So we said let's make small intervals and let's watch that approximate rate function converge onto something, right? Until making the intervals any smaller doesn't change it anymore, right? And then that's when we say we're exact, right? Super small intervals means exact accumulation. Exact net accumulation is found when the approximate functions are no longer distinct from each other. So as delta x gets really, really small, our interval size, then our partial just becomes like the last completed interval. All right? And then we rewrite this in this new form, the integral from a to x. So a can be like any starting value now. And we're going to accumulate kind of like at every rate, right? We're going to accumulate at every rate because our intervals are so small. So that's the whole function. So that's our exact net accumulation. Last principle, exact total accumulation. So we're going to add all the previously accumulated amount to the net accumulation to get the total accumulation function. So anything that's accumulated up to A, we're going to just stick that on as a lump sum. And then starting from A, we're going to track the accumulation using the integral. So what is all the previous accumulation up to A? How do we represent that if the function is f? If our total accumulation function is f, how do we represent all accumulation up to, from before, up to A? Yeah. So at A, it doesn't have to be 0, it can be A. And so how would we represent that, the y value at A? So you got the right idea. It's a function notation, but it's f of A, right? So we're going to add all the previous accumulation plus than our kind of our running total, right? Then we're gonna track the minute changes as x increases from a. And by adding those together, then you get f of x at any moment, or the amount of the function. So that this longer written homework that's due tonight, you're practicing all that whole process, right? This whole process of getting from exact rate to exact accumulation, and you practice using function notation. So this is a really good written assignment that you're working on right now. Any questions? Yes, please.
Why would, in the case of a equals 0, wouldn't the integral already accommodate like that change? Like I get it if a already 6, so if it's 0, the integral already starting at 0.
So if there is no accumulation before 0, so it's possible that your independent variable can track values for negative x values. So f of 0 then would represent like all accumulation for x from negative whatever to 0. But if it's time and you're forgetting about that and you're starting at time equals 0, then your f of 0 will be 0. But that's not always the case. You can have stuff going on for negative x values. Does that answer it? Okay, cool. What else? Good question. Okay, so let's really understand this integral notation. We really want to practice where did this come from. So we want to, whenever we see this expression, the integral from a to x of rf of t dt, we want to think of this from where it came from, right? It came from the approximate accumulation function. Sum of changes from completed intervals plus a little more change from the current interval. But if we're talking about the integral, it's this thing with a value of delta x so small that very small size of the completed intervals makes the partial interval essentially the last completed interval. So we can just disregard that. Or imagine it kind of being absorbed into the sum of the completed intervals. Okay, so now you're going to just take a couple minutes to ask how are they the same. So for each of these items 1 through 4, you're going to identify where do you see it in the first expression and where do you see it from its origin in this expression. So number 1, what part of this reflects number 1? What part of this reflects number 1? Then you go on to number 2. How do you see number 2 up here? How do you see number 2 down here, etc.? So everyone's talking to somebody. You're discussing this. You have four items to identify in both expressions. Go. Okay, we know how fast something is changing. Where do you see that in the first expression? Rf of t, I heard some people say. And the second expression? R of x, right? R of x. Good. So here, the exact rate function or the approximate rate function in the second one, right? That's how fast something's changing. We want to know how much of it we have. How much do we have in the first and the second expression? In the first? Or in this case, how much change we have, how much variation we have in that quantity. So what expresses how much variation we have? Yes, sir? R of t? Well, that was number 1, right? That was how fast it's changing. So now how much variation do we have based on that? Yes, right. And how's that expressed? How do we express the entire thing? With function notation, right? So you could just say the left side of each is how much change we have. Right? How much change is the output of the function, or the dependent variable of the function, which is found by summing up. Where do we see summing up in the first one? Integral. Second one? Summation, right? This is the idea of summing up summing up lots of bits of change. Okay, so now here, this is kind of the most important one, but it's the one that seems hardest for students to get. Where is a bit of change, or the bits of change represented here? We're summing up bits of change, which is delta y or dy's. How are those represented in these expressions? Everyone's got to get this. Okay, yes, sir. Nope, I'm asking for a bit of change. A bit of change. Yes, ma'am.
Is it the RF times dt?
She wants RFT times dt. Because that would be rate times a little change. And rate times a little change gives change in our quantity that we're measuring. That's it. This is what we've been hammering, or the heart of the whole matter, m dx. M dx, right? dy, a change in our quantity equals the rate times a little change in independent. So what I've circled, what I've highlighted in green then, gives a little bit of change. And then we're accumulating those, right? Doing the running total to get, how much net variation up until x. We add up all the little bits of change. So how many, when you were talking with your partner, how many got that number 4 right? Just be honest. How many got number 4 right? Okay, more than usual. Okay, but do you see it now? So make sure everyone in here, super important that we're summing up bits of change. Each bit of change is an m dx, or rate times change. Okay, so we're going to practice then. So now, expressions like these, just generic expressions, you come along to something like this. What does it mean? So now we have a really solid meaning for an expression like this. Anyone want to give it a try? If you just saw this on a page in a textbook, now we know what that means. It doesn't mean, a series of steps to solve something. It has a meaning. What is it? Yes, sir? The net accumulation from 3 to x. What's that? Yeah, good. So he said the net accumulation, so of some quantity, right? There's some quantity that's accumulating, and we're going to track its accumulation starting at 3 until x, where what? Where what's true about the quantity? It's increasing at a rate of radical x, right? Radical x. So I don't want you to just reproduce these words every time. Yeah, so first of all, when you see an integral expression, you think of it as a net accumulation function, like an a sub f of x. So here's one way to say it. I don't want you to just take this template and keep changing, filling in the blanks. Here's one way to say it. This is the exact accumulation of changes in some quantity f due to its variable rate of radical x at every moment t from 3 to x. So what he said in the back was great. This is another way to say it. So the key is that you can say it in your own words. So exact accumulation of changes in some quantity f of x due to a variable rate radical x. And it gives us that exact accumulation at every moment starting from 3 until x. Or at any moment x. Okay, so I want you to practice on these two. Okay, so practice, take turns, get a partner. So first of all, write these down, because I'm going to take them off so I can do attendance. So write those two down, and then you're practicing, not repeating what I wrote, but in your own words. Okay, in your own words, the meaning of each of these expressions. Okay, so just quickly. So this one, What? This is the exact net accumulation of some quantity starting from negative 4.8 if that quantity is changing at a rate of sine x. Okay? This one, when you have 0 to 12, you can think of a function, but a particular value of the function. So this is this a number or a function? Is this a number or a function? This is a number. This is the exact net accumulation starting from 0 and ending at 12, from 0 to 12. If you accumulated at the rate w squared minus 7. So that's going to give you a value. That's no longer a function. That's like a particular function value, a f of 12. Okay? This one, so the volume increases at a rate of 2 over x plus 1. That's our rate of change. We know that at 3 seconds, the volume is 18. So we have a kind of a starting volume. So if we want to do Vx, all the accumulation from before, what is this? This is like V of 3, plus the new accumulated amounts. So from 3 to x of 2 over, not x, need something else, t plus 1. So this is the volume accumulation function. All the accumulation up to 3 or 18 inches cubed, plus the bit by bit accumulation of volume starting at 3, which is our integral accumulation function.